Hi and welcome to this new series where I will highlight some of the interesting stuff from my first game I ever made and distributed on Steam. The game is not a commercial success, and rightfully to be honest, but we will talk about it later. Actually, at the very end of this series I will definitely have a lessons learned episode. Nevertheless, there are a few interesting things I would like to share with you. And today it's gonna be the very physics powering the movement of the balloon. So buckle up and get ready for some elementary school level science. So the traditional approach to moving the balloon vertically would be in every frame you would take the previous altitude and add a new increment calculated based on the magnitude of the user input and something like a climb rate, which is arbitrary number, either a constant or you can use whatever, you can make it nonlinear, you can use curves, and it's a great approach if you don't care about the physics and if the movement itself is not important for the game mechanics, or if you want to keep it really safe and deterministic, or if you want to make the movement somewhat stylized. But for me, in this case, it was really important the balloon's vertical movement is as realistic as possible. It was the very base of the whole challenge for the player to learn to predict the motion with its huge momentums and delays caused by the physics in real world. In this approach, you don't control the movement of the objects directly. You rather set the masses of the objects and apply forces and let the Unreal Engine take care of the movement based on those values. Now, besides gravity, which is taken care of by Unreal automatically, the other important force affecting the balloon is the buoyancy force. That's the force that actually lifts the balloon upwards. It works the exact same way as if you try to submerge a ping pong ball into a glass of water, and you can feel the water trying to push the ball upwards towards the surface. Except in our case, the glass of water is the Earth's atmosphere and the ping pong ball is the hot air inside the balloon's envelope. So how do we calculate this force? Luckily, Wikipedia has our backs, so very conveniently right there, where there is a part talking about an object fully submerged into the medium, there is exactly the equation we need. It basically says that the difference between a gravitational force and the buoyant force is equal to the difference between the density of the medium and density of the object multiplied by the displaced volumes and gravitational constant. Now we are interested in the buoyant force, so let's transform accordingly. And there we go. This is our buoyant force formula. And this is what it looks like in the blueprint. And now you're probably asking, okay, but how do we get the densities? Again, Wikipedia has the answer. The density of air is equal to the air pressure divided by specific gas constant, which is a table value, and temperature. The pressure is a normal air pressure, and it depends on the altitude. In case of my game, it starts with this hard-coded constant at the 0 altitude and loses approximately 12 pascals per meter. The ambient air temperature depends on two things in my game. One is a time of day and also the altitude. It starts with some baseline depending on the time of day and then drops 10 degrees Celsius every 1000 meters. This temperature is also always indicated on the right thermometer. So that was the ambient air density, and now to the balloon air density, to the hot air density. It's still a gas density, so the formula is exactly the same. The pressure is also exactly the same because the balloon envelope is not pressurized vessel. It has the same air pressure as the air surrounding it. And the specific gas constant, obviously, it's still air, so again, it's the same. So the only thing that's different is the temperature. And how does the temperature differ? How do we calculate the temperature? Well, every balloon has a burner. And as long as it burns, it heats the air inside the envelope. So if we take the time of burning and multiply it by the burner power, which is 1 megawatt in case of my game, and then we divide it by the mass of air inside the envelope and the specific heat capacity of air, which again is a table value, we have a temperature difference caused by the burner, and all we gotta do is to add it to the current temperature, and tada, we have a temperature of the air inside. And now very important thing to notice here, this delta time is the actual input from the user in this scenario. So the user doesn't tell the engine directly, go up, go down. The user tells it, heat the air for this long, and that's it. The rest is physics. And of course, when the burner is not burning, the air inside the envelope starts cooling down, eventually gets denser than the ambient air, and the balloon starts descending. And again, this temperature is indicated on the left thermometer and is the most important thing to watch when playing the game. Now a practical demonstration. Notice how the temperature on the left thermometer, on the envelope thermometer, is rising while the user is holding the burner activation button. When it rises enough, we have a liftoff. And then when we let it cool down enough, we start slowly descending. We still need to be using the burner a lot when descending, because when you let it cool down too much, you descend too fast and you die. So that's it. That was the physics of a hot air balloon. I hope you enjoyed. If you did, please hit the like button. It will help me a lot. Don't forget to subscribe because there's a lot more coming, and see you next time.